so let's solve this optimization problem. So let me just restate this optimization problems clearly. So the optimization problem so this is a constraint optimizations. So that means that we want to minimize 1/2 the norm of the weight and norm of so 2 norm of the weight W, then square it out, subject to the constraint. The constraint is yi xi w plus w0 bigger or equal than 1. So we call this is primal problem. Then we can define something called Lagrangian. So the Lagrangian is w0. I'm going to introduce a due variable called alpha here. This is basically we're going to turn this constraint optimization into unconstrained optimizations by introducing these due variables. This is plus sum of I from 1 to n of alpha I 1 minus yi and x of I w plus w0. All right, so this is the Lagrangian. Here we assume this is the due variable has a property with this alpha I is bigger or equal than 0. So this is also called the Lagrangian multiplier. So the key is we can reformulate this primal problem by using the Lagrangian right here. So and this primal problem becomes the following. It's minimax problem. So we have previously we have a minimization problem. So this is a minimum of W and W0. And this is, we can try to maximize of this alpha bigger or equal than 0 of my Lagrangian. So maximize this and the Lagrangian here with a constraint right here, it's equivalent that we can and that we satisfy this and a constraint in my primal problem here. So this is a rephrase or reformulate this primal and primal problem. Because this whole problem, as I mentioned, this is convex and has strong duality as well. So I'm not going to prove this, convexity and the strong duality. I'm just state this right here. So this is convex plus strong duality. So what you can do is you can actually shift the orders of the and the minimization and the maximization here. So this will becomes, I'm going to switch the order of maximization of alpha bigger than 0, then minimization of W and W0 of the Lagrangian. So basically with this condition, we can switch the order of the minimax. So if we look this way right here, so basically we can just solve for and solve for optimal W and W0 as a function of alpha, provided this alpha is bigger and than 0 for each component. Right here, so that means we're going to take partial derivative of my Lagrangian and a partial W. This is equal to right here, so we can just take partial derivative and with respect to W right here. So this is W minus summation of I from 1 to the n and alpha I, yi, and x of I transpose. Okay, so and also there's another component, and that we need to take partial derivative with respect to the W0, which is the intercept. That will be minus summation I from 1 to the n of alpha I of yi. And both I'm going to assign this to be 0. So that tells you this right here, this W star will be summation from I from 1 to the n, alpha I, yi, and x of I transpose. And this is just a summation of alpha I, yi will equal to 0. Okay, so this is some constraint here. And right here we have plugging and find out the expressions for W hat right here. All right, so then we solve the inner and optimization. Then we're going to plug in back to this and the Lagrangian. So then this becomes the following. So we have W hat, W0 hat, and alpha here. So this is equal to. So we're gonna write this is 1 over W hat transpose W hat plus summation from I from 1 to the n of alpha I, subtract and subtract the things that we already here. So we have and plug in W by W hat. So this is let me see. So this is equal to summation of I from 1 to the n of alpha I, yi, x of I, and the W hat, and subtract W0 of summation I from 1 to the n, alpha I, and yi. Okay, so the beauty here is this whole thing is 0 because of this. So everything here is gone. What actually left is these 3 terms. And also, the most important, and another part that we can see carefully here, if we actually factor out, I think there is, so right here, this is nothing but W hat transpose, right? Because of my definition right here, I just take the transpose, that will be the same as the thing in the black box. So that means we have plus half of W transpose W hat. Here is minus W hat transpose and the W hat. So this is becomes minus 1 over 2 W hat transpose W hat plus summation 1 to the n of alpha I. Okay, if we actually plug in this, this will give me the following thing. That is minus 1 over 2 summation. Then we are going to plug in the formula of W hat or W star right here. I think I'm using W hat here. So this becomes I from 1 to the n, and j from 1 to the n of alpha I and alpha j, yi, then yj, x of I, and x of j transpose, plus the summation I from 1 to the n of alpha I. Okay, so that is the cases that we plug in our Lagrangian by the W hat we already solved previously. Then we are going to solve for the outer outer optimization problems. So the outer optimization problems becomes that we need to solve for alpha is bigger or equal than 0. Summation I from 1 to the n of alpha I minus 1 over 2, summation I from 1 to the n, summation j from 1 to the n, and the alpha I, alpha j, and the yi, yj, x of I, x of j transpose. And of course, we have one constraint need to be satisfied subject to this summation of the alpha I, yi equal to 0. So this is something called due problem. So it's basically, you can think about like front side and the back side of one coin. You can solve either way. That will be equivalent. Sometimes primal problem is easier. Sometimes due problem is easier. Depends on the problem settings right here. So this is still, this is another quadratic problem. It's another like quadratic programming. But in this cases, our constraint is simpler because this is a linear constraint right here. And we only have this alpha is bigger or equal than 0. So the constraint is easier. On the other hand, on the primal problem, this constraint is much more complicated. So this is, the constraint is, and we have to deal with an xi and the yi at the same time. But here, it's much simpler and a constraint, and it just needs to deal with the yi. And we know yi is just plus 1 and minus 1. All right, so with a KKT condition, so that means if we can solve this due problem, that we have optimal for this optimal this W and the W hat and the W0 hat and the alpha hat, right? So that implies this so this additional term that and adds on right here will become 0. So what does that mean? So the KKT condition says my alpha I star multiplied by 1 minus x of I w star plus w0. I think I'm using hat here. Let me using hat. This is equal to 0 for all I. So and then the most important part is for alpha I is hat is not equal to 0, and then that implies this right here. Wait. That's just a second. Yeah. I mean, for all the alpha I had is not equal to 0. That means this thing has to be equal to 0. And more precisely, this has to be equal to 1 precisely. But we know this yi is either +1 or -1. That indicate this x of I of w hat is plus w0 is actually equal to hat is either +1 or -1. Right? So that indicate this x of I and the yi is actually a support vector, because that's by definition, we already talked about this. We have and just mentioned, and all the support and the vector lies on the lines which and xw plus w0 equal to +1 or -1. So from experience, you can see, and we will find out that most of an alpha I are 0, and only few are non-zero. And what actually make contribution is those like non-zero part, because those are like support vectors. And those support vectors actually will make contributions to determine where is my margin and where is my boundary condition and the decision boundaries. Everything else is just being 0, has no contributions. Right, so this is give you some idea. All right, so my W hat and my W hat, I want to remind you, this is summation of I from 1 to the n of alpha I hat of yi and x of I transpose. And of course, we can find out the W0 hat accordingly. You can pick any and yk that is on the support vector, subtract to this summation of this whole thing. I. But this will be x I and x of k transpose. So this will, and it will be your W0 star. For any and alpha k and for any alpha k hat is bigger than 0. So these are and corresponding to and k and with xk and yk are support and the supporting vectors. So basically using supporting vectors to find out the optimal W0s. Okay, so, and you can see this is quite ideal because this summation is fast. And most of Wi is zeros. So they're only like very and a simple component that is non-zeros. And here you only need to pick one supporting vectors. Then you can find out the intercept and automatically. So by the end of the day, and all we need to do is try to solve this do problems. And this do problem turns out it's easier to be solved than the original and the primal problems. Okay, so this whole thing in the do problem can be solved with something called SMO algorithm. So SMO algorithm is short for sequential minimal optimization algorithms. I'm going to show how this thing is being done, but this is completely optional to run everything of SMO. It's much more evolved, but I'm going to demonstrate that with the code already being provided, and you try to understand as much as you can. All right, so let me show it to you. Run all. So first thing, we generate some data here. So we are using the scikit-learn's toy data generated of the make blobs. So basically, we make the blobs of two and two blobs. And in total, we have 500 points, and we have two centers. And we are going, and the y here will just be 0 and 1. So, but in SVM, we need to change into +1 and -1. So that means we need to change the class label to be +1 and -1 right here and right here. And we color them with the blue points and the red points. And you can actually plot them out. So this is the data right here. And you can see we have a two blobs right here. One is somewhere here, one is and another one is here. So we are using this sequential least square programming, which is SMO. And you need to use some SciPy and optimization packages. So this is something of SciPy and optimization called optimize.minimize right here. The method that we use is called sequential least square programming. So basically what they do is you need to specify the constraint right here. So the constraint right here is being specified as D minus C alpha equal to 0. So this is an equal constraint, and the second is an inequality constraints. So this, and you have like equality constraints and inequality constraints. The first constraint that we already showed, this is this A in the product Y has to be 0, right? So this is right here. And also another constraint that is my alpha has to be bigger or equal than 0. So that's why you write down this whole thing is so this whole thing is so an A in the product Y has to be equal to 0, and the second one is and this A here is it's basically this alpha has to be equal to 0. All right. So you have some initial condition of a bunch of ones, and this is the Jacobian. You can specify the Jacobian right here, which is Y and A here is just identity, right? So and minus identity. So like minus identity times of and the minus identity, that will be identity times of A has to be bigger or equal than 0. So this is just equivalent to say an alpha has to be bigger or equal than 0. So you have in Jacobian, you have constraint. It just solve it automatically for you. You don't need to worry too much about this. And these are the, and you set some epsilon. If your alpha value is bigger than 10 to the minus 6, so we consider this point is actually the support vectors. So I want to emphasize the support vectors at, as like any distance 1 to this and the zero boundaries, as we mentioned. Okay, so we can also find this like support vectors. Prediction is super simple. This is just a linear regressions. That will be 2 times of this and what is bigger than 0 or not, and subtract 1. So that means if it is true, that will be 1. And the 2 times 1 minus 1, that will be 1. If it's false, that will be a 0. So that means 2 times 0 minus 1, that will be minus 1. So this is just a quicker way to turn from like 0, 1 into 1 and minus 1 to 1. So you run everything, and we find 3 support vectors right here, and this is my my W, and this is my intercept, and we find out there are 3 alpha that is bigger than the threshold, that corresponding to 3 support vectors. In fact, we can visualize that explicitly. So this is actually the and my separator, which is my decision boundary right here, and this is the upper margin line, and this is lower margin line. And the beauty of everything is you can see we circle out these 2 are support vectors, and this one is this support vectors. Everything beyond this actually doesn't matter. It doesn't contribute anything to this decision boundaries, because what actually matters is on those like support vectors. All right, so this is very clear. And this is obviously a very an interesting things to look at that, and it's very convenient, and this illustration is very and very powerful. But I want to emphasize here is to solve this dual problem, it turns out to be simpler than solving this and a primal problem, because primal problem right here that we have to worry about this type of constraint. And this type of constraint is much more complicated. It's much more difficult to be vectorized and write it out and explicitly compared to the dual problems. So for this hard and margin problem, it will be much more simpler if we just work directly on the dual problems. All right, so but let's just make things a little bit difficult. For example, I'm going to add 1 outliers right here. Right, so if I add 1 outlier right here, this original and the decision boundaries right here will not work, because if I still draw a like decision boundary right here, this doesn't perfectly separate this and the red point and the blue point. But technically, you can still separate these and the blue point and red point perfectly as well. You can draw a like line right here and a separate blue and the red. You can still do this and like a margin problem. You can see this actually is very bad, and this is my and the decision boundary right here. I still have 3 support vector here, 1 here, 2 over here. But in this case, your margin is super small, and your decision and your margin like in between is super small. So, and you can see, if I draw a line right here, this is not really a very ideal situation. Okay, so and one way to like tackle these things is we say we don't want these data to be like perfectly linear separable. I say I can allow certain level of the errors. For example, if we can allow certain level of errors, as I can perfectly separate these part and these part, I can allow this red point to be classified wrong. So that means I can still draw a line right here, although I will create 1 error right here, but that is okay. I prefer my and the decision boundaries to be more robust, and versus some line and a line here that is significantly less robust to those perturbations. All right. And you can see this is perfect examples of the bad line right here, as we already mentioned on the first, on the last lectures right here. And this is really bad examples of, decision boundaries. Ideally, the decision boundary should be something like that. So that means this hard margin SVM is not really a good idea, in general. So, and what you can do is, another way is we probably should introducing some kind of regularizations. We will talk about this in the next lecture in detail. So this is something called soft margin and SVM. So instead of hard margin, we want our data to be perfectly separable. We allow certain errors. If we allow certain errors, that we can make our line or the decision boundaries to be much more robust and versus this hard margin problems. So this is examples for the soft and a soft margin. We're going to talk about this later on in detail, but this just I want to show you if we and introduce and if we allow certain level of the error, in fact we can still draw our and the linear boundaries right here. But of course, these two will be the support vectors, and this point right here will be classified as wrong. But that is fine, and we allow certain errors in the soft margins. All right, and we can also validate with additional 10,000 test point for both hard margin and soft margin in these cases. And in these cases, we can find out if we're using hard margins right here. So this is something called confusion matrix. That means if the true label to be blue, there will be, if we're using this line right here, this line here, you can see there will be 4 points being classified as red instead of blue. So that will be, and it create additional errors. And because my data is not, and my line is not robust enough, and it's not it's not, that's, if we, perturb testing data a little bit, it will create more errors. However, if we're using the soft margin idea, we still want to make sure this line is in the middle for the majority of the data, while we can allow certain outliers to be wrong. Then in this cases, we can still perfectly separate the red and blue if we sample those red and blue from my original distributions and without the outliers. Okay, so you can see this is much better way to work with, and hard margin is not a good way to work with. Although mathematically it's quite clear, it's quite beautiful, but in practice you should never use hard margin. Hard margin just give you an idea, if you really want your data to be perfectly separable, and how do you formulate this problem, and how do you solve these problems. Okay, so what actually is look like right here. So for example, this is the testing data. If we're using this and the linear boundary and the decision boundaries, you can see we have 4 points right here, and they're supposed to be blue, but somehow being classified as red, just because this testing data here, and this point is so close to this blue points, and my line right here is so close to this blue point. So if I perturb the data a little bit, it will be classified wrong in these cases. And also, if we consider the confidence level in terms of the logistic regression, the probability actually to be predicted as red and the blue around this line will be super low. So it won't be a really good idea. In terms of confidence and probabilities settings, then these values won't be a good idea, and won't be a good prediction, as won't be a good predictions anyway. On the other hand, if we draw a line right here, like what we did in and the soft margin, as I just showed, this can still perfectly separate the blue points and the red points. So this will be a much more like ideal cases and ideal lines to draw right here for the testing data set. All right, so that's everything about, that's everything I want to talk about for this lecture. In the next lecture, we're going to dig deeper to discuss about, soft margin SVMs.